talked about thermodynamics a lot, but this week we're going to talk about kinetics. And kinetics is a little different from thermodynamics, so it deals with reactions. Let's say, for example, we have this reaction. Again, we go back to this funny box that is called the universe. So we just use that to make connections with thermodynamics. It's related. And let's say we have a system here. So we carve a system in this big universe, and then everything else is surroundings. So this is universe, surrounding system. In the system, what is happening is this reaction. So there's a reaction. And let's just, to make it less complicated, actually for now, I'm sorry. So let's just use a single arrow here. So it's just a forward reaction. It's not a forward-backward reaction. So let's say that it's just a forward reaction. Okay, so what we need for this system, in order to be able to describe it, is to find out the properties of this system, to find the properties, to calculate the properties of this system here. Okay, so as you recall, actually, so if I go back, as you recall, we talked about this last week. So we talked about this equation. So this is the change in the entropy of the system in terms of change in temperature and volume. This is one simple equation that is used when there is no phase transition in the system or no reaction. So S entropy depends on temperature and volume and nothing else when there is no reaction in the system or no phase transition. The same here, S depends on temperature and pressure when there is no reaction. However, when there is a reaction, if you go back to the seminar notes 5th series, so if there is a reaction, for example, let's say entropy or Gibbs free energy, I just wrote here Gibbs free energy. Gibbs free energy depends on temperature, pressure, and also the number of moles of each one of the reagents that are involved in the reaction. So it makes things very complicated. So we have to keep track of every single one of these species, A, B, C, D, any of these reagents in the system, in order to be able to calculate G at any time during the reaction. Okay, G or any properties of the system, for example, entropy, Gibbs free energy, or enthalpy. This makes things very complicated, but it turns out that actually you can link all these number of moles in this reaction to each other by using just one single independent variable. Okay, it's called extent of the reaction. So instead of using all these, instead of keeping track of all these variables in the system, you only need to keep track of this variable, extent of the reaction. That, in fact, extent of the reaction shows the advancement of the reaction. For example, let's look at this diagram here. So let's say the reaction starts from time 0 and then it goes to completion here. Okay, T final, time 0. This is the start of the reaction and this is the completion. At any time during the reaction, you can define xi. Xi is shown actually by this letter, Greek letter. It's called xi. Actually, it's awful because I'm using a mouse here. I'm sorry, but so it's denoted by this letter. Xi for this reaction at the start is 0. So because we haven't initiated the reaction, so it shows the advancement of the reaction. At the start of the reaction, we haven't initiated it yet, so it is 0. At the end of the reaction, it is complete, so it is 1. We're going to use actually this concept a lot in Gibbs free energy, especially in the help session tomorrow. We're going to use this concept, this xi, but maybe not really in the kinetics, but it's used for equilibrium and calculating the Gibbs free energy at equilibrium. So that's why I have to explain this. Okay, so we said that we can link all these number of moles in the reaction during the course of the reaction to each other by this variable or xi, and that's the equation. That's the proposed equation for that. Okay, so the number of moles of any species I, so it could be A, it could be B or C or D, any of the species that are involved in the reaction. So Ni, the number of moles at time t, so that is Ni, is equal to the number of moles at time 0. So this is the initial number of moles here, Ni naught. So this naught here refers to time 0. It's different from the naught that actually we're going to use tomorrow for Gibbs free energy that refers to the standard pressure conditions. So this is different. In here, it's time 0. Ni naught plus minus nu I. So this is called nu. This is shown by letter nu. And then xi. What is this nu here? This nu is the stoichiometric coefficient in the balanced reaction equation in here. What is plus? What is minus? Plus sign is, so it's a convention. Plus sign is used for products because products are produced during the reaction. So whatever you had at time 0, if you produce more and more, for example, C, then it gets added to its initial value. So therefore, it is a plus. For the reactants, we must use a negative sign. Okay. So now, by using this xi, we can replace all these Na, Nb, Nc, all the number of moles, by just one variable here. So G only depends on temperature, pressure, and one independent variable. So this is the independent variable. Everything else, all this number of moles, they are dependent on this xi using this simple equation. So I'm just giving you here some examples. For example, for A here in this reaction, in this reaction for A, so number of moles of A at time t is the number of moles at time 0, negative because it's a reactant. So according to the convention here, so negative. And then what is nu I? It's the stoichiometric coefficient for reagent A in this reaction, which is alpha. Okay, that's the stoichiometric coefficient for A. And then times xi. You can do the same thing for B. Okay, you can relate it to xi using this equation. For the products C and D, the only thing that changes here is this sign. It's a plus. Everything else is the same, just the plus sign changes. Okay, so we talked about xi, but that was to reduce these the number of independent variables or variables in describing this the properties of the system, or describing the system, in calculating the properties of the system. But when we have a reaction happening in the system, there is also another thing that is important to describe the system, which is how fast this reaction proceeds. Okay, that's another thing that is important in order to be able to describe the system. It's the second factor that must be determined in that system. Okay, in order to do that, we have a definition for the rate. So we have different definitions for the rate, and what I'm talking about here is the rate with respect to the derivative of the number of moles, Ni. So that's the definition of the rate with respect to the derivative of the number of moles. We're going to need that actually a lot in the calculations, and I'll show you today. So that's the definition. It's a positive negative 1 over nu I. Again, this is the stoichiometric coefficient of species I. Change in the number of moles of species I over change in time. Okay, and this is not the rate law, so it is important. This is another definition of rate, but it's not the rate law. The rate law, I'll get into that in a minute, but the rate law is an empirical equation. This equation is not empirical, it's a mathematical equation. Okay, so that is empirical, that is mathematical, but they should, at the very end, they should be the same. Anyways, what is this plus for, or what is the minus for? So again, if a species I is among the products in the reaction, then we use the positive sign. If a species I is among the reactants, then we use the negative sign. So it is important. Always positive for products, negative for reactants. But in kinetics, we usually work with concentration instead of number of moles. So Therefore, we divide both sides of this equation by volume of the solution, of the reaction solution. Okay, if I do that, left-hand side, rate over V, we have the rate law, sorry, we have the general rate of the reaction in terms of the concentration, and we show that by epsilon. Okay, so this letter is similar to this one actually, but I just used this curve at the very end. So this letter is called epsilon. This is nu. Okay, this is nu, the stoichiometric coefficient. This one is epsilon, and it shows the general rate of the reaction. So it is rate over V. So if I divide also the right-hand side by V, Ni over V, I showed it here. Ni over V is the concentration. So that is the concentration of a species I, the number of moles of I over the volume. Okay, so that's the concentration. Oh, sorry. Okay, for example, A is Na over V, for example, it's the concentration. So when we put it in square brackets, then it's the concentration, okay, in here, or I. So by doing this, I can convert this to concentration of I. So this is the new definition for the general rate of the reaction in terms of the time derivatives. Okay, so the general rate of the reaction is positive, negative, plus, minus 1 over nu I times di, concentration of I over dt. Okay, so the question is now, what is this di over dt? If we plot this graph, if we plot a graph of the concentration of I, or the number of moles of I against time, okay, in the system, then we normally we have products that change over time following this trend, and reagents, they follow this trend over time. When the time starts from 0, so this is time 0, and this is time final or completion, for example, in here, time final, this is completion. Okay, so the reagents, they start from an initial value, which is non-zero. Of course, we should put some of these reagents, sorry, if I go back here, we put some of these reagents, and then we mix them into a vessel, and then they react, right? So the initial concentrations are non-zero for the reagents. And then as the reaction proceeds, they go down, they decrease in amount or in concentration, and they go to 0 at the very end when the reaction is complete. For the products, they usually start from 0, not always, usually start from 0, and then they increase in amount and until they get to their final values when the reaction is complete. Okay, but what is this di over dt? Okay, di over dt, for example, let's say if we plot the graph of concentration of I against time, then di over dt at any point is the slope of this graph, for example, for the products. For the products, it's positive, as you see here. Actually, the slope is always positive. For the reactants, it's always negative. So that's di over dt. That's the instantaneous rate of production or consumption of I, depending on if I is a product or a reactant. If we go back to this reaction, for example, again, and so this is just an example, and if we write the equation for the rate law now in terms of the partial derivatives, sorry, not partial derivative, in terms of the time derivative, then, for example, let's write the general rate law of this reaction in terms of the change in the concentration of A, for example. We follow this equation, right? So it's because A is a reactant, then we use a negative sign here. So negative sign. Negative 1 over nu I. What is nu I? It's the stoichiometric coefficient, which is alpha here, right? The stoichiometric coefficient. And then di over dt. I here, we replace it by A. So the species A here over dt. We can write the exact same thing, so the general rate for this reaction, but in terms of the change in the concentration of B. So it's similar. Again, negative sign, 1 over beta dB over dt. What about the products? For the products, it's we should use a positive sign. For example, for C and D, we use a positive sign. So what is important, what I'm emphasizing here is that you can write down the general rate for the reaction. And let's say, for example, let's say this is just a forward reaction. To make it simpler, let's say this is just a forward reaction. So you can write down the general rate for the reaction in terms of any of the species in the system involved in the reaction. Okay, any of these species. So that's how we write down the equation for the general rate. Okay. Again, going back to di over dt. Okay, we talked about di over dt, and we said that actually it's the rate of production or rate of consumption. So we talked about this, and we showed that it's the slope on the graph here, the slope here. Okay, and we said that actually if I is one of the products in the system, then we must use a plus sign. If it's a reactant, then we must use a negative sign. If I is a product, then this rate here is the rate of production of a species I, because I is a product. So we're going to use these terms a lot. That's why actually I emphasize them here. So if I is a product, then this is the rate of production of a species I. If I is a reactant, then it is the rate of consumption of a species I. Okay. So sorry guys, actually I have to stop here and see if you have any questions. Do you have any questions, guys? Okay, where were we? So 27. Okay. Okay, good. So no questions. Okay, so now if we can write down the rate of consumption of a species I. So this is epsilon I. It's different from epsilon. So epsilon is the general rate of the reaction. This epsilon here. When we put an index here for a species I, then it is the rate of consumption or production of a species I in the reaction. So these two are different. Okay, but they are proportional, and the proportionality constant is the coefficient, the stoichiometric coefficient for species I in the reaction. So the rate of consumption or production of a species I is the slope here, but with a positive or negative sign. Okay, because because rate must always be positive. So rate should be positive. Okay, for if I is a reactant, if we go back to this graph, if I is a reactant, then the slope is negative. The slope in here is negative. So this ratio then is negative. This slope here is negative. We have to multiply it by a negative sign to get a positive rate. So that's why by convention, they use this negative sign for the reactants. The positive sign is for products. For products, the slope is already positive. This slope is already positive. Again, if we go back here for the products, it's always positive at any time during the reaction. So we don't really need to change the sign of the slope. So it's just a positive sign. Okay. And it is proportional to the general rate by using its coefficient. So if you multiply the general rate by the stoichiometric coefficient of a species I, then you will get the rate of consumption or production of species I in the reaction. For example, I'm just giving you here two examples. Again, if we go back to this reaction, and let's say, just to make it simpler, it's just a single arrow reaction. So it's just a forward reaction. Okay. So the rate of consumption of A. Why consumption here? Because A is among the products. It's one of the one of the reactants. So A is a reactant here. So we use a negative sign, dA over dt. And how we can relate this to the general rate? You just multiply it by nu A, which is the stoichiometric coefficient here, which is alpha. Sorry guys, I'm using a mouse and my handwriting actually is awful here. For C, it's a product, so the sign is a positive sign. And the same thing, dc over dt, but we use the stoichiometric coefficient for C, which is gamma. So this is gamma here. Okay, gamma times epsilon, which is the general rate. Okay, so we're gonna actually use this definition a lot. So the definition for the rate of consumption, that is the mathematical definition for the rate of consumption and rate of production. We're going to use that a lot in reaction mechanism. So one of the questions in the problem set number 4 is, for example, question number 2 is based on that actually. Everything is based on this definition here. And we're going to talk about it a lot more actually when we get into one of the questions that I'm going to explain today. Okay, so we talked about one of the definitions for the rate, which was this one. So we talked about this. So the definition of the general rate with respect to the time derivative. There is also another definition for the general rate or nu, so you can, sorry, epsilon. So you can show it also by epsilon here. Rate. There is another definition which is called rate law. Okay, we used that a lot in labs I, A, and D. You remember that, right? So this is an empirical equation. This is an empirical equation. So it's based on experiments. You can determine the rate of the reaction using this simple equation based on the data that you collect from the experiment. Okay, that's actually what exactly you did in many of the experiments in the labs. Okay, so let's say we have this simple reaction, and let's say it's for example, let's just talk about the forward reaction. So I'm just talking about the forward reaction. So in the rate law, the rate is defined based on the concentration of the reactants in the system. So it is important. Reactants A and B. So if it's forward reaction, then the reactants are A and B. What is K? So I just intentionally put F here, which means rate for the forward reaction. Kf means K for the forward reaction, for example. A is the concentration of A, of course. And what are the exponents A and B here? These show the concentration dependence of the reactants. Sorry, concentration dependence of the general rate. Okay, and of course these concentrations are always the concentration of the reactants. Okay. We can also write the equation for the general rate for the backward reaction. So let's say, for example, we have only the backward reaction. What is that? So what is the general rate for the backward reaction? I just intentionally put B here, which means backward. So we should have another rate constant, and the concentrations are the concentrations of the reactants for the backward reaction. For the backward reaction, now C and D are the reactants. Okay. So C raised to the power of this little c, and then D to the power of D. Again, D and C and K, they are determined experimentally. So determining the rate law actually means determining this K here, this exponent C, and this exponent D. Of course, by using experimental data. So that's determining the rate law. It doesn't matter if it's forward or backward. It doesn't matter. It's the same here, K, A, and B. So if you determine all those three, then you've determined the rate of the reaction, or the rate law. There are many different ways to determine the rate law. Okay, I just remembered, actually, I remembered like last night that I actually left out elementary reactions. In an elementary reaction, so there is a concept in kinetics, it's called elementary reaction. So I put 0, that's the first way, as 0th way maybe. In an elementary reaction, the exponents, for example, let's say if we go back here, so it's like, I should erase this, sorry. Let's just talk about the forward reaction here. Okay, anyways, let's just talk about the forward reaction. So let's say it's just the forward reaction. Oh, sorry. And in an elementary reaction, the exponents A and B here, they match the stoichiometric coefficient. They are equal to the stoichiometric coefficients. For example, in here, A is equal to alpha, B is equal to beta. So that's for elementary reactions. So always keep that in mind. For elementary reactions, it is easy to determine the rate law. The only thing that we need to determine in an elementary reaction using experimental data is this K. Okay, that's the only thing that we need to determine. That's the only parameter that must be determined in the experiment for an elementary reaction. But what if the reaction is not elementary? So that's the question. So there are many different methods. One of them was, and we used it actually in lab I, it's called the method of initial rates. So what happens in this method? So what is the process here? Okay, so the process here is that actually, so what we do here is that, so we collect the data at different trials. So trial, for example, 1, 2, 3, 4. And what happens is that in some of these trials, we keep the concentration of one of the reagents fixed. For example, in trial 1 and 2, 1 and 2. We keep the concentration of A fixed. But what we do here is we keep the concentration of the second reagent. We change the concentration of the second reagent. Okay. So, and then what we use is we use the method of comparison. So take the ratio rate 1 divided by rate 2. So we've collected these data, all these rates from the experiment, or we've calculated them using simple equations from the experimental data. So we've collected these data. So for example, if I compare rate 1, rate in trial 1 to rate in trial with rate in trial 2, then I'm just using the equation for the general rate for this reaction. So that's the equation for the general rate. So it's K1, the rate constant for the rate law in trial 1, multiplied by the concentration of A in trial 1 raised to the power of A, multiplied by B in trial 1 raised to the power of B. The same thing here for trial 2. So what is rate 1? According to the table, it is 0.38. What is rate 2? 0.17. So we've calculated it either, or we've obtained it using an instrument in the experiment, for example. What is the concentration of A in trial 1? It's 5. It's here. And then what is it in trial 2? It's 5. So what happens is that we've kept this fixed, so they cancel. We're only left with the concentration that is different in trials 1 and 2, concentration of B. In 1 it's 10, in B it is 13. So if we do the calculation here, so that is the ratio, and then we use we take the ln of both sides just to bring this power down to be able to calculate B. So if you do the calculation, you can calculate B. In this specific case, B was 3. So and for that, actually, I use this method here. So this method, I put it on the side. You already know about this. And then there are some examples actually to use this method. So example problem 18.2 in the textbook, 3rd edition of Engel and Reed's book. Please study that. And also problem 18.7 and 18.8. So what you do here is that you just keep the so you just repeat it over several trials, and what you do is you keep the concentration of one of the reagents fixed, and then you vary the concentration of the other reagent or the other reagents in the system, and then you calculate the exponents one by one, and then the variant you need to calculate K. You've already learned this in the lab, so I don't really want to take your time with that. But this is the first method that we use, that is called the method of initial rates, and it's based on experiments. And because it's based on experiments, we just use this simple equation, which is the empirical equation for the rate law. Okay, so that is the rate law. It's called the rate law. Okay. So we talked about the rate of consumption of air. Actually, I should show you this now that we've learned about the empirical definition of the rate law. This is the empirical definition of the rate law. So if we go back now to the rate of consumption, the rate of consumption of A in a reaction, it is equal to negative dA over dt. We already know that, which is equal to nu A multiplied by the general rate. Now, if I replace this general rate by the definition that we get from the rate law, okay, this here. So it's nu A, which is the stoichiometric coefficient, which is alpha here. So it is alpha times K multiplied by A raised to the power of A, B to the power of B. I'm sorry here, actually, it's wrong. It should be just forward reaction. In this specific case, it is just forward reaction. I'm sorry, actually, I made a mistake here. So it's just forward. So rate of consumption of A is negative A over dt, which is equal to alpha times K times A raised to the power of A, B to the power of B. We're going to use this again in reaction mechanisms. That's why actually I had to show you guys this. So nu A again is this, and then this is not important. Actually, what I did here, I replaced nu A by multiplied by K by Ka, but it is not really important. Actually, it's we don't really need this. We always use this nu A times K and the rest of it. Okay, so that was about the rate of consumption or production for each one of the species. For example, in this case, I just showed it for A. So, and as I said, we're going to use this a lot in reaction mechanism. Sometimes for a reaction, what we need is, for example, consider this reaction. So alpha A goes to products and K is the rate constant. Sometimes we need to find a relationship between the concentration of A at any time during the reaction with time. So A, how it changes over time. So A and time. So we need that. We need to find that relationship. Sometimes we need that. In order to do that, we use the method of integration. Okay. So the question is, what is A at any time during the reaction? In order to find that, we need a method of integration. Okay. So what happens if I show it on this diagram? So the reaction starts here at time 0. The initial concentration of A, we show it by A naught. Okay. And then when the reaction is complete, we just show it, for example, by T final, and then the concentration is going to be A final. If it's just a forward reaction, it is 0. In fact, if it's just a forward reaction, it is 0. The A final must be 0. All of it reacts to produce products here, P here. Okay. So the question is, what is A, for example, at time T during the reaction? Is this A? So let's assume that. So I'm explaining the method of integration. Let's assume that nu, or the general rate, is first order with respect to the concentration of A. And let's assume that alpha is 1. What is alpha here again? So alpha here is the stoichiometric coefficient. So I'm just assuming one specific case. What is the definition, the mathematical definition for the general rate? Okay, that is one way. That is one way to define that. That is one way. So one way is to use the time derivative. So it's negative because A is reactant is negative 1 over nu A, which is the stoichiometric coefficient, times dA over dt, which is negative 1 over alpha dA over dt. And because alpha is 1, therefore it is 1 over 1. I just don't put it here. So it's negative dA over dt. Okay, so that's one definition. Epsilon. I just keep repeating. I just keep saying nu, but this is epsilon. Sorry, epsilon, the general rate, is negative dA over dt. What is the second definition? The second definition is to use the rate law. Okay, so these two are the same. Epsilon here is the same as the epsilon here. I'm just using two different ways, and that is the method of integration. So the second method is to use the rate law. K A raised to the power of A, and A is 1 here because it's first order. We've assumed that it is first order. So A here is 1. This is 1. So this is the second one. In the method of integration, what we do here, we set these two equal, and then we integrate. So we set this equal to this because they both give the general rate, both of them. So negative dA over dt is Ka. Okay, that is the method of integration. So in order to integrate this, we have to collect terms that are the like terms. We have to collect them on one side. For example, this is dA, and we have A here. So collect them on one side. Same here, K doesn't depend on anything, but we can just put it here on the right side with T, which makes it simpler. And then if you do the integration here, then you get this equation. Okay, if you do the integration, it is already in the lecture notes. Okay, so for the integration, it goes from a initial. So maybe I should. Sorry. Okay. Anyways, so in here, actually, the integration goes from a naught to a, so a naught to a, and time goes from 0 to t. Okay, it goes from 0 to t, and then if you do the integration, you get this equation. And if you go to the formula sheet, that's the exact same equation. So page 3, that's the equation. Okay, this is the equation for the first order reaction. This A naught here is the initial concentration of A. Okay, times exponential raised to the power of negative kT. Okay, so that's the equation for the concentration of A in terms of time for a first order reaction. And we've derived it here, actually, okay, using the method of integration.